All right, ladies and gentlemen, we're going to leave. We're going to do what? We're going to pick up where we left off. I don't know why that was so hard to say, but I got through it. Starboard. So, hello. There we go. We did this reaction last time, and it was called halogenation of an alkene. And we're using a mixed halogen here. We didn't have to, but we did. And its name gives a hint about how it reacts. Bromonium chloride. Why is it called bromonium chloride and not chloronium bromide? Does it, at the end, anions end with "ide," right? I know this is not ionic, but it's named a little bit like it is, isn't it? Cation, bromonium. Can you name other cations that end with I-U-M? I want two. Ammonium, nice. And that's NH4 with a plus, right? And what's the other one? pKa -3. Oh, the general category ends with IUM, oxonium. The parent of the category, H3O+. Hydronium also ends with yum. Yum means plus, right? So why would they say bromonium? Because it's the one that has it has a lower electronegativity, which means it's slightly positive. You don't have to show me slightly positive and slightly negative in mechanisms. You don't have to. But it does explain why, when we did the mechanism right before the exam, and we told you it wasn't on the exam, we attacked the less electronegative atom, right? And then the other one gets kicked off. And unlike reacting with HCl, unlike those reactions, this one has lone pairs, and they come back to which of the two carbons? The one with a higher degree sign or the one with a lower degree sign? Higher, because it's a better carbocation, right? Hyperconjugation. So those were our arrows last time, and we made a triangle. You remember that? No, you didn't, because you didn't study it. It wasn't on the test. I understand. Okay. Don't forget, there's a copy of the activity right there. You got it? Okay. So we're going to do something similar in the new one, which is below it. It didn't ask for a mechanism on the one above, so I gave you one for free. It wasn't asked for. I just want to see how similar it is to this next one. When you have water present, adding water to the above reaction creates conditions for halohydrin formation. And I forgot to mention in this morning's video why this is called a halohydrin. I think you know half the reason. You know the halo reason. There's a halogen on it, right? But I bet you didn't know a hydrin is an alcohol. It's old school for alcohol. And yes, we have an alcohol there as well. And not only is water added, but it's also the solvent. Water is also the solvent. And a lot of people, when they're first learning chemistry, take for granted how the implications of that word, solvent. Okay, it's the medium of a reaction. It's the environment, right? But the most important thing is everything is dwarfed by the amount of solvent. Any other amount is tiny. Solvents have a huge concentration, right? Because it's the main liquid in there. So when I ask you what base is going to show up first, water or, in this case, bromide, which one are you going to answer? Water, because it's everywhere. Why? Because water is also the solvent. Okay. And there's another reason why we're going to use water as a base near the end of this mechanism, and I want to save that surprise. Okay. Because water is the solvent, the chemicals water and Br2 have already reacted with each other. They're sitting in the back room in a bottle labeled bromine water. And they reacted when you made the solution. So that's part of your mechanism, to show the reaction of water with bromine. And it comes in and it boots off the other bromine. You generate this species here with bromine. We'll put it in blue. No, it looks like it's black over there. Water's in blue. Lone pairs on there. Other product really is not going to be used because there's not much of it and it's not a very good base. I'll give you a preview. Can you tell me the pKb of Br minus? Do you remember how to work it out? 14 minus some number, right? Minus the pKa for the base's conjugate acid. What is this base's conjugate acid? What's the formula? HBr. What's the pKa? Nice. She was rolling there, -5. This is about as bad a base as you can think of, right? So when I ask you, why does Br minus not react? You're going to tell me, well, its pKb is too high. It doesn't like reacting. That's for later. The part that's coming up now is going to look so much like the top reaction that you're going to say, yeah, I think I better know that reaction. The pi attacks the less electronegative Br. The pi attacked the less electronegative Br up here. Here it was 2.8 versus 3.0. Here it's 2.8 versus 3.5. Hey, guess which one's faster? Top or bottom? The Br is even more positive down here because of this bond to a much more electronegative atom. That Br is much more positive, so the reaction is much faster. The pi electrons are attracted to the Br much more because the Br is much more positive. Okay? And then the sigma breaks and creates not Cl minus like the top of the screen, but what are we creating there? With that second arrow? Don't be afraid to say it. Oh, you need a handout from the back. Oh, she got it. Sorry, never mind. What are we creating with the blue piece? H2O, also known as water. We made a triangle. I'm gonna put way over here. We got our triangle. We got the original will be purple. We got Br. We made 2 bonds to Br, right? Those are just real, those are bonds. There's our required marks along the side of the screen. I'm sorry? Yes, you should copy everything. Even these names, cyclic bromonium ion. Makes sense. It's got a cycle with a triangle, and it's got a plus charge on the bromine, right? And what's the other piece? The thing that got kicked off in blue? H2O. Now you realize there's a lot of water. It doesn't have to be this one that we just made. It could be any of the waters that was floating around before that does this next step. And you know water has to do it. Look, where do you think OH came from? It didn't come from Br minus, right? Had to come from water. So we're going to come in at an angle that's 180 degrees from the bond you're breaking right here. Sadly, I chose red for my arrows and I do a rare switch to a pink arrow just for contrast. And we had a name for that called backside attack. You remember that? You don't have to write the words backside attack on a mechanism, but I'm trying to jog your memory. It's not the first time we've seen this before. And what you get is your triangle's gone. So you got rid of all that strain. And your OH is on a big fat wedge. And the O still has two H's. And Br, I didn't break this bond at all. It's still there. You got to tell me what to do to get from there to there. What kind of reaction is it to get from here to here? What kind of reaction removes a proton from a species to make it? I don't want to give it away with the words in my question. I kind of did it already when I used the P word. What kind of reaction is it? Do you remember when I mistakenly said the P word? That's almost the answer right there. Well, we didn't hear the P word. What are you removing from this molecule to make this molecule? Not just a hydrogen atom. No, I didn't use that word. Deprotonation was exactly what we're doing here. What kind of reaction is that? When you're talking protons, it's always this kind of reaction. It's a whole chapter in the book, reaction. It was on our last test, Monday reaction. You can even calculate the equilibrium constant for it. If you knew the base, oh, I just gave the answer. No, that's half of it. What do bases react with? Acids, what kind of reaction is it? Acid-base reaction? Acid-base reaction? You need to tell me what's the best base to take the proton off of this acid to make it into its conjugate base. And you got to review your words because they weren't coming quick today. I know it's the day after a test. We're all kind of just, we're just lucky to be here, you know. But yeah, we got to know what acid base is. We got to know there's an extra proton here. It's the conjugate acid of this. And you got to tell me what the best base is to take the proton off. And if you say Br minus, you totally missed the point of why I brought up Br minus having such a high pKb. You missed the point. There's a much, well, 100 times better base here that's available in much higher quantities. What base am I talking about? It's the number one thing people ignore with the word solvent. Now I know nobody's been paying attention. Water is the solvent, yes, but what's the number one thing about the word solvent that people take for granted? The concentration of the solvent dwarfs that of any other species. Replay this video. There's a good use of the word dwarf. Maybe you've never heard that use of the word dwarf. It means it just outweighs it by a large amount. Okay? There is so much water, and water's pKb. Here's your redemption opportunity. H2O, I need the pKb calculation, please. Give me the numbers to do the math and then do the math for me. Oh, the same mistake was made this morning. You're not following the same procedure you did here. Where did this -5 come from? It did not come from Br minus at all. Where did the -5 come from? You were the one that came up with it. Why did you come up with it? the conjugate acids pKa. Please don't give me water's pKa. Please give me the conjugate acid of water's pKa. Please. They are the second strongest group of acids in this course. -2 or -3. We'll go with -3, just for fun. It's hydronium. 14 minus -3 equals 17. So why is water a better base than a bromide? Lower pKb means stronger base, okay? And there's a lot more water than Br minus. There's one atom of, or ion of Br minus here. There are 55.6 moles of water per liter available. That is the concentration of water in water, okay? So yeah, it's not even close. Water's your best base. Does that mean this is going to be the first semester that nobody uses Br minus as the base by mistake? I hope so. There we go. And you made your vicinal halohydrin. I didn't use the word vicinal yet, so let's just pretend it's a halohydrin for now. I'm saving the word vicinal maybe for Wednesday. Okay, now we got to fill in some stuff, some blanks. All right, I want you to focus on Cl and compare it to Br. Is Cl more or electronegative than Br? More. So the more electronegative elements ended up on the blank substituted carbon. Once again, I want more or less. And substituted is just a fancy way of saying which one has a higher degree sign, the carbon with a Cl or the carbon with a Br, tertiary or secondary. Tertiary is the more substituted carbon where Cl is. Same story downstairs. The more electronegative elements, which is oxygen, 3.5 versus bromine, 2.8. The more electronegative element ended up on the more substituted carbon again. And what's the name of that? Whenever that happens? Markovnikov regioselectivity. Good word, regioselectivity. Which region of the alkene was selected for by each element? Yeah, that's it. And when it's Markovnikov, more and more. We'll see anti-Markovnikov at the end of today for the first time. And there's another type of selectivity that has nothing to do with which group goes to which region. No. It's which group goes on which side of the alkene. One of the groups is in front of the alkene, and one of the groups is behind. How do you describe that? Anti. The two new groups are on opposite sides of the skeleton. Wedge dash is the best way to do it. Same story down here. The two new groups are here and here. Opposite sides of the skeleton, wedge dash. And I believe we've accomplished everything we set out to accomplish. And there we go.